so just be careful what we say. It will be posted on YouTube, so if you want to go back and reference anything, you can go back, check the video. My study guide, do note that this is more of a study aid than a guide, so I don't have any insight at what is going to be on the test. So these are just problems that I believe Medeiros covered that is relevant to what could be on the test. So don't only study this. I encourage you to also study problems from the book or his lecture notes and anything else. So the agenda for today is we're going to go over the study guide. I'm going to start with more of the relevant material. So I'm going to go over shear moments, centroids, moment of inertias. And then if we have time at the end, I added a frame problem, and I also have a truss problem. So if we have time, we'll cover that as well. So we'll begin with a shear moment. So what's the first step for a shear moment? Free body diagram. Very good. So what's going to be on our free body diagram? Yeah, so what type of support do we have at A? A pin. So what type of reactions do we have? AY and AX. So AY, AX. What about at B? What type of support is that? It's a roller. Very good. And what type of reaction do we get? Only. So the proper way is we have a reaction that is perpendicular to the surface. So it doesn't mean it's always going to be in the Y. So it's perpendicular to the surface. So, but in this case, it is Y. So we have a couple moment at the end. And what about that distributor load? How can we put that on our free body diagram?
There's a concentrated load 6 feet away from A.
So how do we simplify that distributor load into a 1/2 base times height? So that's how we find our FR. So that's the equivalent force. So 1/2. So what's the base? 9 feet. Very good. And what is our height? 50 pounds per foot. That's 4.5. And that comes out to 225 pounds. So now what's the distance going to be? How do we determine that distance? Yep, very good. So it's 2/3 from the light end or 1/3 from the heavy end. So that's going to be 2/3 of 9, which is 6 feet. And the magnitude is 225 pounds. All right, so now what do we do once we have the free body diagram? So what does everyone think? Do we start making section cuts yet? Yeah. Very good. Yep, so we find our reactions. So what do we know about AX? It's 0. Since there's no loads being applied horizontally, it's only AX, so therefore AX is equal to 0. Very good. So now how do we solve for AY and BY? Yeah, so we could take a moment about A, we could take a moment about B, but we're going to do about A. So what causes a moment about A? Very good. So does everyone see that? So using the right-hand rule, this 225 pounds causes a negative moment, and that's acting 6 feet away. So what about anything else? BY. Very good. So what does everyone think? Does this couple moment cause a positive or negative moment? Negative. Yep. So it's a clockwise, so it causes a negative moment. And what is this all equal to? 0. Very good. So just adding the 200 and the 225 times 6 over and dividing by 9, we get BY is equal to 172.2 pounds. So does everyone feel comfortable solving that so far? Yeah. I'll try and write a little bit better. So now, how do we find AY? Yeah, so solving with forces. So if you like taking moments, you could take a moment about B now and solve for AY, but typically solving with forces is a little bit easier. So what forces do we have acting in the Y direction?
AY plus 172 equals 225.
Yeah, very good. So I just wrote the 225 on one side. But yeah, so I substituted BY in as 172.2. So AY, so adding this over and subtracting 172, we get 52.8 and the units of a force is in pounds. All right. So now we have our support reactions. Now what's the next step? Breakpoints. So how many breakpoints will we have? 3. Why 3? Yeah, so we'll have them one at the end, one at the beginning, the end, and then since this is a continuous function up to the support reaction, we have one at the support or at the end of the distributor load. So we have one at the beginning, the support, and the end. So now we have our breakpoints. Now what can we do? Cuts. So we cut in between the breakpoints. So since there's 3 breakpoints, we have 2 cuts. So now we'll draw the free body diagram of cut number 1. So we always have our support reaction, which we calculated as 52.8 pounds. In which direction is the shear going to be acting? Down. So positive convention for the right side is downwards, and for the moment, we have it acting counterclockwise. So I'm going to call this V1 and M1. And now what about the distributor load? How do we draw that? Do we draw it as this 225? No. So since this distance is some arbitrary distance x, it's not the total length of 9 feet. So you can't just write the simplified 225. So it's going to look something like this. But the key part for the distributed loads, for the triangular ones, how do we now determine this height? So the height originally was 50 pounds per feet, but that was at 9 feet. How do we determine it at a distance of x feet? Yeah, so one way is we could do similar triangles. So the original one was a height of 50, acting at 9 feet. So if we have a similar triangle acting at x feet, it's going to be y. So now using similar triangles, we could say y over x is equal to 50 over 9. So y is equal to 50 divided by 9 times x. So does everyone see how to do that? So it's essentially, you're just finding the slope of this line. So the other way you could do it is rise over run. So your rise is 50, your run is 9. Your where it crosses the y-axis is 0, so mx plus b, you have your m, rise over run.
And then you have to divide it by 2, right?
Why is that?
It's a triangle, and then the force would be half that.
Yeah, so for the force, we have to divide it by 2. But this is just the height of this at any distance x. So if you want to check if that's right, you could always do times it by 9 feet, and you do get 50 back. So the 9s will cancel out, and you get your load of 50. All right, so now we have this height. So now how do we simplify this distributor load into just a single equivalent force? So now we could use 1/2 base times height. So the FR is equal to 1/2. And what's your base? X. Very good. Now what's your height? 50 over 9, and that's times x. So that will simplify to 25 over 9 x squared. So now we have one resultant force as opposed to that distributor load, 25 over 9 x squared. And now what distance is that acting from this cut point? So we're not taking it about A anymore. We want it from that cut point. So I hear 2/3 and 1/3. So we're taking it from the heavy side, no longer from the light side. So since we're taking it from the heavy side, it acts 1/3. But if we take it from A, it would be 2/3.
You can do both sides if you want, right?
What's that?
You can do it from either the left side or the right side.
So typically we take the moments about the cut point, so it's just more convenient to have it from the cut end. But yeah, so that's the way we're going to solve it. So it's 1/3 x. So is that everything we need for this cut section? Anything missing? No, it looks good. All right, so we want to solve for our shear and our moment. So which one should we start with? Does it matter? No. So we can start with either. So for ease, we're going to start with the sum of the forces in the y, which is equal to 0. So what forces do we have acting in the y direction?
We have the 52.8.
Yeah, so I heard shear, and so that's acting down. Then you said this 52.8, which is acting upwards, so it's positive. And then,
And then the 25.
yep, and this is acting downwards, so it's negative. And now we could just add V over, and we get our shear equation. 8 minus 25 over 9x squared. So anyone have any questions on how we solve for that?
Just because I can see it's 25 divided by 9, right?
Yeah, so this is 25 divided by 9. So that's our shear equation. So now how do we find our moment? And this is shear 1, shear 1. So we could take a moment about the cut point. So I'm just labeling it as m dot. So m dot just refers to the cut for me. So this again is equal to 0. So does the shear cause a moment about the cut end? No. So since it passes through that cut right there, it doesn't cause a moment. However, we still have to include our m1, and that's positive using our right-hand rule. So now, how do we include this equivalent load? What is that going to look like in the moment equation? Yeah, very good. Did everyone hear that? So it's a positive moment from this cut end. So we have our force of 25 over 9 x squared, and then multiplied by the distance of 1/3 x. So can everyone see this? Should I write a little bit bigger? Everyone see it? Yes? Yeah, I'll write a little bit bigger. So right now we have our moment, m1, times our load, multiplied by its distance. And now what about this 52.8? Positive or negative moment? Negative. Yep. So we have our load of 52.8 multiplied by a distance of x. And that's all equal to 0. So now if we add these to the other side, we have m1 is equal to positive 52.8x. And we could simplify this. So we have 25 over 27 x cubed. And a good way to double check to see if your moment equation is correct. So a relationship, does anyone know the relationship between the moment and your shear? Yeah, so the moment equation is the integral of your shear equation. And opposite would be your shear is the derivative of your moment. So if we take the derivative of our moment with respect to x, so this x will go away, we just have 52.8. And if we take the derivative of this, we pull out the 3, so we have 25 times 3 divided by 27, x squared, which is this. The 3 will cancel with the 27, so we have 9 left on the denominator. So that's a good way to double check to make sure your equations are right. Yes?
So instead of like doing all of that, would it be faster if we could just like take the integral of the v after we find the shear for each, for like everything? Sometimes there might be a constant.
Yeah, so depending on like if there's a reaction, you have to know what your plus C is. So Medeiros didn't teach us that way, so I don't want to like try and cover it right now.
You could do the derivative of the moment.
Yeah. Yeah, you could find the derivative of the moment, but you just have to be confident that your moment's right. So in what x values does this range from? So, yeah, 0 to 9. So when we use these equations, we can't use this for the entire beam. We can only use it in between our breakpoints, which is 0 to 9. So x ranges from 0 to 9 feet. And is that it for our first section? Anything else? Anyone have any questions on it? Can everyone read it? No questions? All right, we'll move on to the second cut. So since this is our origin, for our second cut, we still need to include this left side of the beam. We're not only using in between the breakpoints. So I'll write it in a different color, so red and green. All right, so our second section, we'll have the entire beam. And what should we include on there? Yeah, so now that our distributor load is before our cut, could we take the simplified version of it? Yes. So now that we have our full load, we can use the equivalent load of 225. What else needs to be included? BY, very good. Point 2. What else? Yeah. So this will be V2. We're using the same convention, M2. And now we need our distances. So the easy one is the total distance is x. And what about, so since we want our distances from this cut end, what's the distance from this equivalent 225 force? So I want it from the cut end. Yeah. So very good. It's x minus 6. So since we know this distance is 6 feet, if we want it from this other end, we do our total minus our known distance of 6. So this distance is x minus 6. And what about the 172? Yeah, so similarly, it'll be x minus 9 from here. So does anyone have any questions on this? How we derive those distances? No? All right. So we'll start by summing the forces now. So similarly with this, we'll sum, I'll try and write a little bit bigger over here. And y is equal to 0. So what forces do we have? 52.8 minus 225 plus 172.2 minus shear. So we just have our two support reactions, our negative shear, or our negative equivalent load, and then minus our shear load, V2. So does someone want to plug that in a calculator for me? It adds up to 0. So does that make sense? So does it make sense that we would have 0 shear in this end over here? So if we had a shear in here, we have nothing to counteract that shear, right? Because there's no support at the end. So if you had, say, negative 20 shear, there's nothing to react. So therefore, it wouldn't be in equilibrium. So it does make sense that there is 0 shear at the end. Yeah. So once we do our moment and shear diagram, we'll see that this By will bring it back to 0 shear. So V2 is 0. So now if we sum the moments, I think this is the rather tricky part of this section. All right. So what causes a moment about this cut end? So do we have plus or minus M2? Plus, yeah. So M2, and what about this 172? Is it negative or positive moment? Yeah, so it'll be a negative moment. Right-hand rule causes a clockwise moment. So it's 172.2, and we multiply that by x over 9. Or sorry, not x over 9, x minus 9. That's the distance from the cut end. And what about 225? Positive or negative moment? Positive. So we have 225 multiplied by its perpendicular distance of x minus 6. And lastly, what about 52.8? Positive or negative moment? Negative. So 52.8 multiplied by its total distance of x. So does anyone have any questions on it? Can you see it, or is it too low? Move it? Yeah. Right here. So can everyone see the equation? Everyone see how we got each term in the moment equation? So we have 3 forces that cause moments, and we have our M2. And we have 4 variables in there, so that makes sense. So if we simplify this, we could add all these other terms over, distribute our forces into the x minus 2 and x minus 9. 1 second. So our moment equation simplifies to M2 is equal to that make sense that it would be a constant? Yeah. So if our shear, we know that's the derivative of our moment, we know that this would have to be a constant. So if you take the derivative of a constant, you get 0. So, and what values do these range from? So what values can we use that in our shear moment? Is it from 0 to the end of the beam, or is it between our breakpoints? Yeah, so it'll be between our breakpoints. So the first set of equations were between these two breakpoints. Now our second set of equations are between the second and the third breakpoints. So these x values are from 9 to, what is it? 13. Very good. 13 feet. So does anyone have any questions before we start our shear moment? So I'm going to try and draw them on the doc cam. That way everyone can see it. So can everyone see it? Does anyone need me to clarify? All right. So we'll start with our shear moment. So on the exam, on that graph paper he gave you, the top one will be your WX function, which is the, he should be providing it in the EPC. So when you go to the EPC, just, I don't know if you have to mention you're taking statics, and they should provide the paper for you. So that, I don't have it, sadly, but, so your WX function will be the original distributor load. So the beam with the distributor load and the moments. So we'll start with our WX. And what are our units for our shear? Pound. So shear is just a force. So you'll want to label your units. All right. So now, using the first equation, which was for our shear of 52.8 minus 25 over 9x squared. So what you'll want to do is you'll want to plug in your bound conditions. So your first one is at 0. So if we plug in 0 to that equation, what value do we get? Yeah, so we'll get 52.8. So this value, 52.8. And now if we plug in 9 to that equation, what value do we get? So let me hopefully that's a little more clear to read. So if we plug that into our equation, at a distance 9, we get, God bless you, negative 172.2. So what type of function is it? Is it a straight line? Is it cubic, polynomial? Or what type of polynomial? Yeah, so it's just going to be parabola. So is it going to be concave up or concave down, though? Because that's critical. Concave down. Yeah, so if we look at our equation, we have a negative x squared here. So it's a downwards parabola, so it's concave down. So it'll look something like this. So the incorrect way would be if you had it this way. So upwards, but that's not the case here. So what's key about this graph? Is there anything particular about it? Are we done with this shear?
No, that 172.2 is equal to By, so it's going to bring up to 0.
Yeah. So if we look at our end conditions, so if we look at 0, our AY, if we remember on the board, it's 52.8. So starting at 0, it actually brings us up to our initial location. And now if we look at distance 9, we have BY, which is 172.2, which brings us back up to 0. So this differential shear is equal to 172.2, which is what our support reaction was. So in the end, your locations, if they have a support, it should, since it's a force, it's equal to your differential shear. So that's why this brings us back to 0, and this brings us up to 52.8. You don't have to, no. It's just, you want to be artistic, you could. But yeah. So one thing to note on this, though, this is pretty blurry. But one thing to note is it crosses the x-axis. So what does that mean? It crosses. What purpose does that serve?
It's going to be a maximum or minimum.
Yeah. So since this is the derivative of our moment, it's going to be a max or min on our moment graph. So does everyone kind of see that? So we'll need to know what that x value is. So how do we find where this crosses the x-axis? Yeah, so you set this equation here equal to 0 and solve for x. So doing that, you'll have 52.8 minus 25 over 9 x squared is equal to 0. So you'll just add this over, divide out this, and square root it. And since we're on the positive side of the x-axis, you'll take the positive root, not the negative, of course. So that x value turns out to be 4.36, and our units are feet. So once we get to our moment equation, we'll plug that value in, and we'll find what our max or min value is. Yeah, 4.36. And then what was our shear between 9 and 13 feet? 0. So to finish it out, I don't really need to do anything, but so our shear between 9 and 13 is 0 based off of V2 over there. So does anyone have any questions on our shear? So what do we need to finish out this graph? Is it complete? Can you guys even read that? Pretty blurry, but yeah. So one thing you also want to add, so that Medeiros requests, is that you put your function on each set. So since this one is just a constant of 0, we don't need to say it's 0. Pretty clear. But however, this one, so the function is 52.8 minus 25 over 9 x squared. And so that's the function of that line. That's bad. All right. So we have our shear, we have our units, we have our values, we have our x location marked where it crosses the x-axis, and we have our units. So now moving on to our moment. What are the units of a moment in this case? Pound feet. So just like we did with our shear, we'll take our equation and plug in our boundary conditions. So is it 0 and 9? So what's the moment at 0? Yeah, so it's just 0. So if we look at our equation up there, we have 52.8x minus 25 over 7x cubed. So if you plug in 0, your moment will end up being 0. So now what about if you plug it in at 9? 400.02. What's that?
I got 400.02.
So does someone want to double check that number? Plug it into M1 equation, the red one. What's that?
140.7. Negative 199.98.
Yeah, so negative 199.98. So I'm going to round that to negative 200. So at a distance, x is 9. We have our value of negative 200, and that's pound feet. However, since we determined there's a min or max, we also want to plug in this 4.36 value into our equation to know if it goes downwards, if it goes upwards. So someone want to plug that in and give me the value?
Maximum, I got
153.5. I'd agree with that number. So we have a max as positive 153.47. And so using these points, we can kind of say it's going to go something like this. It's going to hit that point and then go back down. And then just like we determined, that is our max. So our derivative there is equal to 0. There's no slope there. So does anyone have any questions so far in solving the first part?
How'd you get the maximum again?
So, yeah, very good question. So the max, so since our shear, we had it equals 0 at 4.36, so that means it's either a max or min. So we just plug in this 4.36 feet, which is our x distance, into our moment equation. Good question. That's 153.47. And then now moving on to the second one, M2, we have a value of negative 200, so it's just a constant negative 200 all the way from 9 to 13. And in order to close it, we could see that we have this couple moments of 200 pounds-feet, so that will close off our graph, which makes sense. It should go back to 0. I don't believe so, no, because it doesn't really serve us anything here, because we're not taking another integral. But yeah, good question.
So on the graph, when the moment is negative, it's counterclockwise.
Yes. So it's a little bit tricky, because if we look at this moment, so using, our normal convention, it's a negative moment, but yet we're going upwards. So it's just kind of opposite. I don't know the actual reason behind it, but so that's the way to think of it. For your moment, so since we have a negative moment, just think of it opposite, and it closes it. Yeah, it could be it. And then, so to finish this off, we need our function, which was 52.8x minus 25 over 27 x cubed. And then, just for clarity, this differential moment is 200. So does anyone have any questions on how to get the shear and moment equations, the plots, how we found the maximum point? Yeah.
Do we have to draw like a line from the shear down to the moment?
So like this line here.
No, like for the max?
This?
Yeah.
I do it just to kind of show that way I don't have to put this is at 4.36 feet. It just, this dotted line, if you mark it here, then he should know that it's constant all the way through. Yes?
For the moment diagram, why didn't we return to, why did we go directly across to the
Right here?
Yes.
Yeah, so our first equation gave us these points, so it gave us a 0, our max, and our min. And our minimum was, at 9 feet, was negative 200. So now jumping to the second equation, it was a constant negative 200. So that's at any point between 9 and 13, we have a value of negative 200 for the moment. And then to bring it back up to the x-axis, we have our couple moment of 200. Yes?
Sorry, how did you find the moment equation?
For which one? Both of them, or?
I'm sorry, just for the first part.
Yeah, for the first part? Yeah. So for the first part, we have we have our 3 breakpoints. So we have 3 breakpoints, so we made 2 cuts in between the breakpoints. So for the first graph, our free body diagram, we have our distributed load. But since it is not the total load of 50, it's at any value of x. So do you know how were you here when we solved for our max? Okay, yeah. So we know at 9 feet, our max value is 50. So in order to get any distance x, we had to use similar triangles. So we know at 9 feet, we have a value of 50 for our y. So at any point x, we have a height of y. So using those relationships, we got our height. And then using the FR is equal to the area underneath the distributed load, we have 1/2 base times height. So that gave us this 25x squared. And it acts 1/3 x from the tall end, or the heavy side. And then for the moments, we have M1. So we're taking it about the cut point. We have a positive M1. And then we have this distributed load, which was, or the force of 25 over 9 x squared multiplied by its distance, 1/3 x. And then lastly, we have this negative 52.8 times x. And that's how we got that equation. And we did the same thing for this one, except it worked out to negative 200. So does anyone have any questions before we move on to a centroid or moment of inertia? Good? All right. So we're going to start with a centroid about, so what type of problem is this? Yeah, so it's a composite shape, and the question is asking to find x bar and y bar. And of course, we're measuring from the axis. So our x bar is going to be this way, measured from the axis, and our y bar will be measured this way. So whatever it ends up being. So what are our equations? So does everyone want me to write on the doc cam or the whiteboard? Just for clarity. Whiteboard? Yeah, it seems pretty blurry. So does everyone have this? Good? All right. So what is the equation for our centroid? Does anyone have that off the top of their mind? This isn't working. So. Yeah. Yeah. So if we do y bar, our equation is the sum of the individual areas multiplied by the y tildes divided by the sum of the areas, which ends up being the total area. So, and then similarly, our x bar is equal to areas multiplied individual x tildes. And what is x tilde and y tilde? Yeah, so those will end up being the centroid of each individual shape. So if we redraw our shape real quick. So how many shapes can we make out of this to simplify it? 3. So I'm going to break it up this way to make it easier. So we have 1 triangle and 2 rectangles. So let's start out by marking our distances. 60 millimeters. This one is measured as, So this total distance is 60. This top one is 30. So therefore, 60 minus 30 to get our base for our triangle is 30. And we have this as 100 millimeters. We have our height of 50 millimeters. We have this height as 40. All right, so let's call this area 1, or shape 1, shape 2, and shape 3. So what's the area of our first shape? Yeah, so 1/2 times our base, and our height will be 40 plus 50, so times 90. Yeah, so divided by 2. I want this one. So does someone want to plug that in for me? 750. So did everyone else get 750? Very good. So for this one, you got 750? Yeah, so it comes out to 1,350. Yeah, so A1, I'm going to write this off to the side. 1,350, and what are our units? Yeah, so it's just millimeters squared.
Wait, how did you get
1/2. So the area?
Is that 50?
90. Because our height is 50 plus 40,
Okay.
so it's the total height. Yeah. So area 2, how do we find the area of 2? Base times height. So 30 times a height of 90. Someone want to plug that in for me?
2,700 millimeters.
Thank you. And area 3. So again, it's base times height, 100 times 50. (5,000 millimeters squared). All right, so let's start by solving for x bar. So x bar is the distance, so it's going to act at some distance from our origin. So using this equation, we have our individual areas, A1, 2, A3, multiplied by their x tildes, so their centroids. So area 1 is 1350. And what is its x tilde?
One third that side.
So is it 1/3 from this side, or is it 2/3? Yeah, so it's 2/3 from this end. So it's 2/3 times 30.
What exactly does x tilde mean?
So x tilde, so does anyone know what x tilde is?
It's the x-centroid of each individual shape.
Yeah, so each shape has its own centroid. So like this is y tilde 1, which is 2/3 times 30. So does everyone see how to get those? And then similarly, for a rectangle, it acts right in the center.
It's the centroid from the origin, right?
Yeah, so it's a centroid from the origin. So for the first one, we have 2/3 multiplied by 30. And then now we move on to area 2. So what is the area of 2?
2700.
Yeah, so 2700. And what is?
Centroid is at 45.
So does everyone see that the centroid is at 45 and not 15? So we're measuring all these distances from the origin. So you have to do 30 divided by 2 plus the distance of 30 before. So keep that in mind. It's not just the centroid of just the shape. It's measured from the origin. So that distance will be 30 plus 30 divided by 2, which is 45. So keep that in mind when solving these problems. It's always measured from a certain location. So now, area 3, we determined is 5,000. And what is that centroidal distance?
110.
Yeah, so we have our 60 plus 50. So 100 divided by 2 is the centroid of this shape plus the distance from the origin. So 110. Very good. And this is all divided by all the areas, which is just the total area. So it's the summation of A1, A2, and A3. So we have 1350 plus 2700 plus 5,000. So does everyone want to plug that in and tell me what the value is? And then, meanwhile, does anyone have any questions how we found all those values?
It comes out to 77.18.
Someone want to confirm that number? Comes out that way? Yeah. Point. Round it to 72.2, and it's in millimeters. So does everyone see how to do it for composites? So we'll move on to the y now. So we'll write it down here. So y bar. So area 1, using this equation, 1350. And what is that y tilde for area 1?
50 over 3.
Yeah. So now we want it. Yeah. Oh, this is x tilde. This one is y tilde. So it's measured from the x-axis. So y tilde is 1/3 now of this total height of 90. So 1/3 times the height of 90 plus the next area, 2700. And what is that centroidal distance for area number 2?
45.
Yeah, so it's 45. So unlike the x bar, we had to add the previous one. All these are measured from the origin. So they're all touching the bottom. So therefore, we don't have to add any additional numbers.
So it's half of 90.
Yeah, so it's just half of 90. So 90 divided by 2. And then lastly, we have our area 3 of 5,000. And what is that distance for y tilde? So it's 50 divided by 2. Yeah, so 25. And then that's divided by the summation of all the areas, which is equal to the total area of A1, A2, and A3. Someone want to plug that in the calculator, please? So, who said 31.7? You didn't. Someone want to double check that number?
I got about 29.7.
Yeah. So it should come out to about 31.7. Yeah, and looking at these values, do they make sense? So should y tilde be pretty low compared to a higher number? Yeah, so if we look at it, it's basically how much mass. It's the distribution of mass. There's more mass on the bottom than there is on the top. So therefore, your y bar should be lower. And then similarly with the x bar. So it should be closer to the center, since a lot of your mass is located in the center. So it's just a way to double check. So does anyone have any questions before we move on? All right. Yes.
Okay, so now I know that the axes are on the bottom and like on the left. Now let's say like the x-axis was on the top of the highest rectangle thing. So would you have to like, how would you do that from the x?
So you're saying
Yeah.
measuring from here down?
Yeah, because like on the homework that he gave us in math thing, like some of them were from like different areas, different axes.
Okay. Yeah. So the question is, what if we wanted our, so this one would be y tilde, or y bar prime to all this. So how would we calculate it then? So we would still use the same equation.
The distance from the x prime.
Yeah, so it's just the distance from our x prime axis now. So now we still have the same area for A1. So it would be A1 multiplied by its centroidal distance. So since we're at the top of the triangle, it would be 2/3 down. So it would be 2/3 your height of 90 multiplied by the area. And then if we go to A2, we still have the same area, and its centroidal distance is still half since we're at the top of it. So that would be 90 divided by 2. And lastly, this distance, we would have,
40 plus 25.
yeah, so we'd have the 40 plus the 25.
So you still have to add the distance tags.
Yeah, because we're measuring from here plus this. So similarly, when we did over here from the y-axis, we had to add all these prior to it. Good question. All right. So now we're going to move on to centroid of a function versus composites. So does anyone have any questions before I erase this? Make sense? All right. All right. So we have our function. Which is y is equal to x 2/3 to the power of 2/3. We have a total height of 4 inches, a total length of 8 inches. And the question is asking, determine the centroid about the shaded area. So what is going to be our equation for determining x bar and y bar? So what does everyone think? So the first suggestion was the integral of the area, y dA. So which one is it? So it's x. And then this will be x tilde, right? So what's going to be our area? So the dA, in a sense. But is this the finished equation? No. So what else? Yeah. So we still need this part of the equation. So similarly, when we did our composites, but is this for the y bar? Is this x tilde? Yeah. So the original one was correct. It is y tilde. However, for centroids, that's when we use yes. Yeah. There we go. So centroids, we still use y tildes, but for moment of inertias, you use the opposite. And those would be squared. So what differential element do we want? So what are we going to use for our dA? So what does everyone think? So does it matter? Could we use either or?
It does. We could.
Yeah, so we could, but yeah. So which one's going to be easier to work with? If we do a vertical bar or a horizontal bar? So a point that Medeiros made in his class is if we choose this vertical bar, we don't have to worry about any gap. So if we took a horizontal bar, we'd have to worry about, this is 8 minus this distance now, right? So for this example, we're going to do a vertical bar. Yeah. So now, what's our differential area? What does that equal to? So, yeah. So our base is dx. And does everyone see that our height is going to be y? Does everyone see that? So at any point along 0 to 8, this is going to be our dA. So dA is equal to y dx. And what is our y tilde? So what does everyone think? What's going to be our y tilde of this area?
1/2 of y.
Yeah, so since we're saying that's a rectangle, our y tilde is the centroid. So y tilde is equal to y divided by 2. So since it's the total height of y and the centroid acts in the center, it's y divided by 2. Does everyone agree with that? Everyone have any questions on it?
How do you know it's exactly on the
So similarly, when we did our centroids, we know a square, its centroid acts in the center. So for the rectangle, it's the same way. So y tilde is the center of that differential element. So now we can plug this into our equation. So y bar is y tilde, so I'll write it over here, is y over 2. So we could substitute that in. We could substitute our differential area, which is y dx. And what are our new bounds? What are the bounds going to be? 0 to 8. So does everyone agree with that? So yeah, we're taking the integral with respect to x, so therefore we want our x boundaries from 0 to 8. But we're integrating with respect to x, and we have y values, so we want to substitute those. Yeah. So we'll just simplify this real quick. 0 to 8 is y squared over 2 dx. And what do we substitute for y? X to the 2/3. So, yeah, so we substitute this in, and then we square it. So 0 to 8, we have x. Since y is equal to x 2/3, given as our function, we also need to square this, though. Dx. And what is that squared? Yeah, so for powers, you multiply them, but if you do multiplication of powers, so like x squared times x squared, you add those. So keep that in mind. That'll come in handy later. Yeah, so this will be x to the 4/3 over 2. And we're also missing the bottom. So we're missing the denominator, which was the integral of dA, which is y dx, 0 to 8. And we substitute y in, x to the 2/3 dx. And just bring that over one more time. All right. So does anyone have any questions so far? No? Okay. So this simplifies to 0 to 8, x to the 4/3. And we could pull this 1/2 out since it's a constant. Dx over, write this one more time. So what's the integral of this top one, of the numerator?
It's going to be
So what's going to be the constant? What do we pull out? So the 1/2 is already in front. So we take the integral 4/3. Yeah. So it's 3/7. So it's 4 plus 3 divided by 3, and then you take the reciprocal of it. And then we multiply by x 7/3. So it's 4/3 plus 1, which is 7/3. And that's ranging from 0 to 8. And then similarly with the bottom, we take the integral. So we have 2/3 plus 1, take the reciprocal of it. So we have 3/5. And that's to the 5/3, 0 to 8. So does anyone have any questions on how we got that? So then you just substitute your bounds. So we know if we plug in 0, we're just going to get 0, so we're only going to plug in the 8s. So we have 1/2 times 3/7. That's 8 to the 7/3 divided by 3/5, 8 to the 5/3. What value do we get? What's that? 1.43. So one answer is 1.43. What are our units? Inches. So does that make sense? That our y bar is lower? So does everyone think? I'll let everyone finish copying real quick. Yeah. So we got an answer of y bar is 1.43, which makes sense. Since most of our area is lower, it should be below halfway, which would be 2. So this answer makes sense. So anyone have any questions before we move on to x bar? Okay. So x bar. And that equation is what? What's the equation for x bar? dA. Very good. Thank you. So now what is, or should we use the same rectangle? Or should we swap it? Yeah, we could use the same one. So same point we made at the beginning is if we use a horizontal bar, we have to account for that gap. So we're going to keep the same area. So we're still going to use this dA as y dx. However, what is our x tilde going to be? What's that? So 1/2 x is one suggestion. So we have 1/2 x and just x. So to the center, so that distance x tilde is just equal to x. So since we're measuring from the origin, the center of that, so since it's differentially small, we're saying the distance to the center is just x. What's that?
Can you explain why?
Yeah, so we know for a rectangle, the centroid acts in the center, right? And this is a differential element thickness of dx. So that's just, not even a thickness. So if we want to measure that from the origin, so at any distance, this is going to be x, whether it's here, here, or anywhere else. The center of that from the origin will just be x. Unlike this one where it was y divided by 2 at all distances. So you don't have to divide by 2 here because it's going to be x no matter what. So does everyone see that? So setting that up is probably the most essential part, is make sure you get your x tildes and your dAs right. So plug all this in. We have x tilde is equal to x multiplied by our dA, which is y dx. And what are our bounds? Yeah, so it's still, we kept the same differential area, which means we're integrating with respect to dx still. So even though we're finding, unlike we found y bar, we integrate with respect to dx, we're using the same area. So for x bar, it's still 0 to 8 because we have a dx there. So that's the numerator, the denominator, 0 to 8, y dx. And what do we substitute for y? Yeah, so we just substitute our function, which is x to the 2/3 dx. So now what is x times x 2/3? Yeah. So a common mistake I've seen is that people will just multiply the two. So don't do that. So when you're multiplying two x's or two y's with some powers, you add those powers. So unlike exponents, where you multiply, when you have multiplication, you add. So does that make sense for everyone? Yeah, so it's 3/3, 2/3, so it's 5/3. So 0 to 8, x 5/3 over 0 to 8, x 2/3. So does everyone understand how to get there? Okay. So what's the integral of that? Of the top, so the numerator? What's that? X 8/3. Everyone agree with that? Yeah. So don't forget the constant. It's 3/8. Yeah. Yeah. So 3/8 x to the 8/3. Ranging from 0 to 8. What about the denominator? Yeah. So 3/5 x to the 5/3. 0 to 8. And then, so similarly, these are just functions of x. So if you plug in zeros, you'll get a 0. So we're only going to plug in the 8s. So we have 3/8 times 8 to the 8/3 divided by 3/5 8 to the 5/3. And what value do we get?
I got
5. So did everyone get 5? So does an answer of 5 make sense? And this is inches. So most of the area is on the right half of this graph, or this function. So it makes sense that our x bar should be past our center, since most of our area is on the right half. And that makes sense. So we got an answer of 5, which is greater than 4, which is the halfway point of 8. So x bar is equal to 5 inches. And is everyone familiar with these terms? Those two hashes for inches, one hash for foot. Yeah. Yes?
Are we always to assume that x bar is going to be like greater than y bar and we have to solve for both?
What do you mean? So like
Like in the last like two things that we did, like x bar was just greater.
it just happened to work out that way. So
It's just because they're
yeah.
lower to the ground.
So to follow up with that, so say we wanted the area, we're not going to solve it, but say we wanted the centroid of this. So the inverse, or not the inverse, but the top half of it, we would think that our x bar would be closer to the origin, right? And our y bar would be here. So it's most of the area up there. So our y bar would be higher than our x bar. It would be a greater value. So yeah, good question. Any other questions before we move on to a moment of inertia? Yes.
So for the one you just drew, the red graph,
Yes.
what would be, just like looking at it, what would be like the easier DA?
So in this case, either one should probably be fine, just because there's no gaps. So if we took this area, or actually there's a gap this way. So we found this element here. Our area would be dy times x, whereas this one, this would be dx. And what would be our height of that rectangle? Yeah, so it would be 4 minus y. So it may be easier to work with this one. So does everyone see it's 4 minus y? Since there is a gap there, so I misspoke real quick. But yeah, so maybe this one. So it's always best to try and avoid them, but sometimes they can't be avoided. So any other questions before we move on? No? All right. So moment of inertias. Is everyone comfortable with moment of inertias? Still iffy? All right. Does anyone need a picture of this before I erase it? All right. These markers are awful. All right, so this marker works. So this question is asking to find the moment of inertia about both the x and y axis. So this height is 8 inches, and the base is 2 inches. This function is y, x to the third, and it's about the shaded region. So what is the equation for moment of inertia about the x-axis? Or, yeah. So what's the general form of Ix? Yeah. So does everyone agree with that equation? So similarly, what is Iy? What is that equation? Yeah, so it's x squared dA now. And then with that. So with centroids, we said it doesn't really matter which differential area we make. It may be easier one without a gap, but it didn't really matter too much. But for moment of inertia, does it matter which direction you take your area, whether it's a vertical bar or horizontal bar? So which one's going to be better to work with?
The one that's parallel to the axis you're trying to.
Yeah. So does everyone agree with that? Has anyone confronted that yet? So it's always easier. So if you're taking the moment of inertia, say about the x-axis, you want to choose an area that is parallel. So since these are both parallel, so what will be the area of this differential element? Yeah. So the height is dy, and the base, the base will just be x. Does everyone agree? Yeah. So we'll start with Ix. So dA equals x dy. So now we could plug that into our equation. Y squared x dy. And what are our bounds?
0 to 8.
Yeah. So since we're integrating with respect to dy, we want our y bounds, which is 0 to 8. And then, so we're integrating with respect to dy, so what do we substitute for x? Yeah, so y equals x cubed. Similarly, x equals y to the 1/3. So you just cube root it. And we substitute that into our equation. 0, 8 y squared times y to the 1/3 dy. And how do we simplify that? How do we simplify y squared times y to the 1/3? Yeah, so we add the exponents. So always keep that in mind. So when you multiply 2, you add the exponents. So what do we get when we add those exponents?
7/3.
So what does everyone think? Yeah. Yeah, so it'll be 7/3. So 2 is equal also to 6/3. So then, but you guys said 7/3, right? Okay, yeah. So it is 7/3 dy. So does everyone understand how to get the 7/3? Yeah. So it's 6/3 plus 1/3. And what is the integral of y to the 7/3? Very good. And that's integrated from 0 to 8. So if we plug 8 in, so similar with the last problems, we plug in 0, you get 0, so we'll just plug in the 8. So we have 3/10 y, which is 8 to the 10/3. What value is everyone getting? What's that? Yep. Very good. And what is What are the units of moment of inertia? Yeah, so it's length to the fourth, and we have inches, so it's inches to the fourth. So does everyone understand how to do moment of inertia? All right, so guide me on IY. Should we take the same differential area? Rotate it? Why no? Yeah, so very good. So we will always want it to be parallel to the axis. Well, ideally we want it parallel, but sometimes it doesn't work out that way. So what happens if we don't take it parallel, we take it perpendicular? Yeah. So the reason we choose parallel is because if you use perpendicular, you have to do parallel axis theorem. So you have to take the moment of inertia, in this case it's a rectangle, plus the y tilde, or this will be x tilde squared dA. So that's why we choose it parallel, to avoid that. So what is our new dA? What's that? So this is dy. Let me write this in a different color. I don't know where my green one went. Up here. So I'll redraw it down here. So we're taking a vertical bar. So the giveaway is your base is going to be dx. But what's the height of this?
8 minus y.
Yeah. Yeah, so the key thing to understand is this gap here, that distance is y. So if we want the height of this, we'll do the total height, which is 8. So we'll have 8 minus y. Does everyone agree with that? So that's a key part to understand. If you have a gap, then you have something subtracted by something else. And in this case, we do have a gap. Whereas before, there was no gap. It was measured directly from the axis. So does everyone see that? That's a critical part. All right, very good. So our dA is equal to what? dx 8 minus y. So now we can plug it into our equation. We have x squared, 8 minus y, dx. What are our bounds? 0 to 2. So now we're integrating with respect to x, so we use our x bounds, 0 and 2. And we're integrating with respect to x, so we want to get what are the y. So what do we substitute for that y? Yeah, so our original function was y equals x cubed, so we directly substitute it. 0 to 8, x squared, 8 minus x cubed, dx. So we can, oh, nope. Good catch, thank you. Yeah, so it's 0 to 2 bounds. So we can distribute that x squared, 0 to 2, so it's 8x squared minus, and what is x squared times x cubed? X to the 5th, not x to the 6th. So x to the 5th, and that's a, yeah. Does everyone agree with it? Everyone follow? Any questions? Yeah. So now, what's the integral of 8x squared? Very good. So you just pull, it's 2 plus 1, and put that on the denominator, so 8 over 3, x cubed. And what about x to the 5th? What is? Yeah, very good. So it's 1/6 x to the power of 6 from 0 to 2. So you just plug in your 2's. So your IY is equal to 8/3 2 cubed minus 1/6 2 to the 6. What does everyone get? 10.67. Got the same thing? Yeah. And then units are to the inches to the 4th. So IY is equal to 10. So does it make sense for IX to be larger than IY in this case? And if so, why? Yeah, very good. So did everyone hear that? So from the x-axis, the area stretches much farther than from the y-axis. So that's one way to double check if your numbers seem right. So Ix should be much larger than Iy, because from the x-axis, it only goes out 2 inches, whereas the y-axis, it goes up 8. So that's just a way to double check between the two values. So does that anyone have any questions before we move on? Everyone understands moment of inertia, centroids, everything? All right. So so the last 3 problems I have another beam problem, I have a frame problem, and a truss problem. Does anyone have a preference? So we kind of covered like the more relevant material, but some of the older. I don't have any worked out, but so the way we would do it, we won't solve it, but kind of show you if for some reason you wanted to choose the parallel axis theorem on one of these. Yeah, or you had to, because sometimes the integration on one may be difficult, so you choose the parallel axis theorem. So say, let me get rid of this, actually, yeah. So say we're taking Ix, and we chose, I'm going to choose this one, actually. So to make it no gap. So we want the moment of inertia about the y-axis, and we said this area is x dy. So what equation would we use? Does anyone know the parallel axis theorem equation for integration? Nope. So we're taking it about the y-axis. So, yeah, so the parallel axis theorem would be this. So DIY is equal to DIY of the rectangle about its centroid. So that's the moment of inertia of a rectangle about its centroid. Does anyone know what the moment of inertia about a rectangle is? Yeah, so it's 1/12 base times height cubed. So what is the base about Iy? So that, yeah, so we're looking at it this way. So our base would be the dy, and our height would be the x. So that's kind of the tricky part. But if you took it about the x-axis, your height would be dy, and your base would be the opposite. So diy would look something like 1/12 base, which is dy, times your height cubed, which is x cubed. And that's the first part of it. So now, what is our x tilde in this case? 1/2x. Yeah. So if our total length is x, the y tilde for a rectangle is just half of the height. So our x tilde is just x divided by 2. So then we would plug in x over 2 squared, and our differential area is x dy. So, and then we won't finish it out, but then your Iy is equal to the integral of diy. So then you would plug in this whole term into your integral, and whatever, depending on what you're integrating with respect to, you'd have to plug in those particular bounds. So if for some reason you want to choose that, it's useful to know, just in case if you have tricky integration on the test, you could resort to this, and it may ease that. So, does anyone have any questions on that? No? Yes? It's clear? All right. So, as a raise of hands, does anyone want to go over a truss? A frame? Frame? Okay. So, by the majority vote of 3, we'll go over frame. So, does anyone want to take a picture of this before I erase it? No? All right. And then if anyone does decide to leave early, if you could just fill out the survey and then leave it on the desk before you leave. Yeah, just put it over there and it'd be appreciated. Yeah, thank you. All right, so we'll go over this problem here. So we have a 50-pound force. We have a pin at A. This is point C. And we have a couple moment at A of 600 pounds per foot. We have several distances. This is 3 feet to C, 3 feet between C and D, and 2 feet between D and E, and a height of 4. So the question is asking to determine the support reactions at A, D, and E. Can everyone see that free body? Keep writing small, but this one? Oh, 500, yes. Good catch. 500. I'll write it in red to show. Yeah. So, are we missing anything? Or does that look pretty good? All right. So, yeah. So the question is asking to determine the support reactions at A, D, and E. What type of reactions do we have at A? So it may be hard to see. Yeah. Yeah, so it's a pin connection. So we have an AX and AY. What about D? What type of support is that? Roller. Yeah, so it's DY. So it's perpendicular. So it's DY. And what about E? Yeah, it's a pin again. So, yep. So yeah, EX and EY. So since we're saying this whole thing is in equilibrium, we could say each one of these members is in equilibrium, right? So if we draw the free body diagram of the first one, we have AY, AX, we have a couple moment of 600 pound feet. And what is our reaction going to be at C? How so? Very good. Yeah, so our reaction at C, the key point to see here is our reaction is going to be perpendicular to the bar. So since that force of this pin is being exerted, so our reaction will be, we're just going to label it as C. It's going to be perpendicular to the bar. So similar with like a roller, it acts perpendicular. So what angle is this going to act at now? Or what are the sides going to be? So we have our supports. We know this distance is 4. I think I heard someone say it. We know this is 3 feet. So what is the hypotenuse of that going to be? 5 feet. It's a 3, 4, 5 triangle. So now, what are the directions of C going to be? Yeah. So essentially, this is 90 degrees. So if you have this as a 3, a 4, and a 5, the perpendicular will be the opposite. So you basically swap the 3 and the 4. So this will become the 3, this will become the 4, and that will become the 5. So it's just 90 degrees, so it's essentially rotating it. So this will be the 4, this will be the 3, and that will be the 5. All right, so now how do we solve for those reactions? Can we solve for it, or do we need to go to, we'll draw the second free body diagram. So that's of member, say 1, this is member 2. This is 500 pounds. This is C. So we determined D has only a Y, and E has a Y and an X. This is 2 feet in between. This is 3 feet and 3 feet. So what is the support reaction going to look like on member 2? What does everyone think?
Dx is 0.
So we have to draw, we're missing the C reaction.
Oh, yeah.
So which direction is that going to act?
It's going to act 3 up and 4 left. Like
So is it going to act in the same direction? No, it has to counteract it, right? So it's equal and opposite. So therefore, our C is going to be, let me move this 3 feet here, is going to be this way, right? So if member 1 is putting a force this way, member 2 should be putting the opposite force. Does everyone see that? How to get that? And then, so what is this triangle going to look like? I'm writing it pretty small. Move this. So let me make it a little bit larger. So this is 3 feet. So what are the sides of the triangle? What's the bottom one? Yeah. So it's going to be the same as this one because it's acting along the same line but just opposite direction. So it's still a 4, a 3, and 5. And then the magnitude will say a C. So which member should we start solving for? Member 1 or member 2? And why? Yeah, so you can do that. So he's suggesting we start with member 1. And so the reason is, how many unknowns do we have in member 1? 3. How many unknowns do we have in 4? Or in member 2? Yeah, kind of said it. It's 4. So we only have 3 equations. We have the sum of the forces of the x, sum of the forces of y, and sum of moments. But we have 4 unknowns. So we're going to start solving member 1, since we have 3 unknowns. So the first suggestion was to take a moment about A. And does anyone know why we're taking about A, not any other location? Yeah, so it gets rid of 2 of your support reactions, gets rid of AX and AY. Since they pass through the moment of application at A, they cause no moment. So what terms do we put in here for our moment equation? So is it going to be negative or positive 600? Negative, because it's clockwise. So negative 600. And what about C?
5C.
So someone said 5C. What does everyone think? So what's that?
It's perpendicular to that bar.
Yeah. So this force is perpendicular. So we know a moment is its force times its perpendicular distance. In this case, its perpendicular distance is the hypotenuse of 5. So very good. And does it cause a positive or negative moment? C. Positive. Yeah. So about A, it causes it counterclockwise. So it's 5 times C. So therefore, God bless you, C is equal to what?
120.
Is that right? Yep. Okay. So C equals 120 pounds. So now what's next? What else can we solve for? Yeah, so we can solve about X or Y. So since C is the magnitude, we can project it into its X and Y components. So we'll just start with the sum of the forces in the X. So what do I put in there? What goes in that equation? AX. Yeah. So since we're taking the X, we want the 4 over the 5. So one way to look at it is like you want your one that's parallel with the axis you're taking it. So the 4 divided by the hypotenuse.
On that triangle, how come the 4 is on the bottom? Like, how come you set it up like that?
Because it's perpendicular to the other one, so its legs are touching.
Yeah.
Oh,
So our original one, so the one about our member, is a 3, 4, 5. So now if you want it perpendicular,
it's off.
you're essentially rotating these two. So this goes on the top and this goes on the bottom. So like if we rotate that triangle, the hypotenuse is still 5. This gets rotated 90 degrees. So that goes to the top. This gets rotated 90 degrees. That's 3. So That's one way to look at it.
Thank you.
Yep, good question. So, and it is acting in the negative direction, so it's negative 4/5 c. So we could substitute 120 for c, and what is AX equal? 96. And what are the units? Pounds. Does everyone see how we got those? All right, and then lastly, sum of the forces in the y equal to 0. And what forces do we have acting in the y direction? What else?
Plus 3/5 c.
Yeah, very good. So it's acting upwards, and it is 3/5 c. So therefore, AY is equal to what? Negative 72. Yeah, very good. And now, say there's a question on the test that asks for the magnitude. So what is the magnitude of the reaction to A? Yeah, so the magnitude is equal to the square root of AX squared plus AY squared. So does someone want to plug that in? Yeah, so the magnitude comes out to 120 pounds. What's that? Yeah. So the magnitude is AX squared plus AY squared and the square root of all of that. So you get 120 pounds. Anyone have any questions so far? No? And then say the question asked you, so let me just draw this out. I haven't calculated this, but so we have AX acting in the positive direction, AY in the negative direction. So AX is, say, 96 pounds. This is negative 72. So your resultant force is acting this way. If I asked you to find theta, how would you find theta? So I may say, what is the direction or the angle this resultant force is acting from the positive x-axis? So how would you find theta? Yeah, so tangent theta is equal to your opposite, which is your 72 over adjacent. So does everyone see that? Of course, this is negative. And then you would just do inverse tangent. So that's not too critical in this problem, but it's good to know how to solve for it. All right. So now we have our support reactions. At A, we still need D and E. So we can jump down to member 2, since we solved for C. So now we have three unknowns, and we have 3 equations we can use. So C is equal to 120 pounds. So how should we first start solving? Is there anything particular we have to use? Can we do anything? Yeah. So we could take a moment at E. So that gets rid of EY and EX since they pass through it. And all that's unknown would be dy. We could also sum for the forces in the x right away. Since there's only one unknown in the x direction, we could solve for that as well. But so since someone suggested the moment about E, we'll do that. So what forces cause a moment about E? dy. What is that in the equation? Is it negative or positive? Negative dy times 2. That's its perpendicular distance, its moment arm. What about, so let's skip C and let's go to the 500 first. Is that positive or negative moment? So the 500, yeah. So it causes a positive moment, very good. Times, what's its perpendicular distance? 8, yeah. So 3 plus 3 plus 2, 8 feet. And now C. How do we take that moment? So you had mentioned the y-axis. What about the x-axis?
The x-axis is going into E, so it's not causing.
Yeah, so does everyone see that? So you could break C down into its x and its y components. However, the x component of this C force passes through E. So therefore, that projection does not cause a moment. So the only one that causes a moment is your y projection. So does everyone see that? All right. So what does that look like in our equation? What's the projection of C onto its y-axis? So 3/5 times C, which is 120, times its perpendicular distance of what? 5. Yeah, so 3 times plus 2 is 5 feet. And is that a positive or negative moment? Positive. Yeah, because it causes counterclockwise rotation. And is that everything? Yeah. So what is, someone want to calculate that for me?
I got 2,180.
Yeah. So I was waiting for someone to say it. So it is 2,180. So it is a large number compared to, say, C, which is 120 pounds, but dy does come out to be that large of a number compared to everything else. So if I asked you what is the magnitude of d? Yeah. Yeah, so it's only one term. So it's this squared, the square root. So, but say this was negative, the magnitude would come out to a positive value. But in this case, it's just that. So now, yeah. So we could sum the forces in the y. What do we put in that equation? Ey, positive y, plus dy, which is 2,180. So is it plus or minus? So which direction is that acting? Is the projection of y? Downwards. Because C is acting this way? Yeah. So its projection is negative. And is that 3/5 or 4/5? Yeah. So it's the one parallel with it, so it's 3/5. Times its magnitude of 120. And is that everything? No. Yeah. Positive or negative 500? Negative 500. So EY comes out to what? What's that? Negative 1620? What's that? Oh, okay. This? Okay. And what are the units? Pounds. So that's EY. All right, and last part, EX. But we sum the forces in the x direction. And what forces do we have acting in the x? So does C in the x direction cause a positive or negative force? Positive force, yeah. And then, like you said, it is 4/5. So 4/5 times the magnitude of 120. EX is equal to what? Negative 96. Everyone else get that? Negative 96. And again, that's in pounds. So if the question asks what's the magnitude of the force, reaction force at E, how do you find that? Yeah. Weird. What does that come out to?
1610.9.
So 1610.9, and that's in pounds. So that would be the magnitude of E. Very good. And that solves the problem. So the key part of it was to know that you could break these into its individual members and solve them individually using equilibrium. So if the whole system is in equilibrium, then each member is in equilibrium. And then the second key part was knowing that the reaction force caused by the pin is perpendicular, or whatever, yeah, the pin acting there. So any questions on that problem? All right. So I think that about concludes solving problems. So if anyone has any questions, whether it's a problem that we solved today or any other questions in general, we don't really have too much time to solve another one.
So what are some things that we did not cover in this session that we could review?
So another thing would be like equivalent systems. So is everyone done with this so I can erase it? So yeah, so if you can take a beam and solve for the shear moment diagrams, then you should be pretty comfortable solving for equal or equivalent systems. So yeah, so it's like, you don't have to copy this down. This is just an example. So if you had, say, a pin here and a roller, so this is A, this is B, and you have some moment and some force, and you want the equivalent force and moment at A, you would just sum the moments, or sum the forces in the X and Y direction, but since there's only a Y, so the equivalent force would just equal to the forces, and then the one trick is, in equilibrium, you set it equal to 0. However, for equivalent systems, you just solve for the magnitude, or the total, the summation of it all. Does that kind of make sense? Yeah, so you're not solving for like the reaction force, you're solving for an equivalent system. So if you had a bunch of forces, what you're doing is you want to make it into, say, one force in one moment, acting at one location. So that's the purpose of equivalent systems, is you're trying to convert numerous forces into one force, and numerous, we only have one moment here, but into just one equivalent moment. So that would be something else that could show up on the test. So,
Forces play into the equivalent moment too.
yeah, so if you take the moment, you have this moment and the moment generated by the forces. So that's another thing that could show up on the test. Yep.
Okay, so this was something like I didn't know for the last thing. Are you supposed to take the reaction and then add it all together to at the A?
So for equivalent systems,
Yeah. So you're not okay. So you're like you try to solve for the reaction at A and then add all the other forces.
so what does everyone think?
Wait, no, that would just equal 0.
Yeah. Yeah, so for equivalent system, you don't have to worry about the support reactions. You care about the external loads. So you care about this force, and this moment. You don't worry about the reaction forces. Because you want to convert these forces into just one force. So that's the purpose of it. And then you could solve for your support reactions after if the question needed. But the equivalent systems, you just try to simplify it. Yeah. Another problem that would show up is potentially a moment of inertia of a composite shape. So like finding the moment of inertia about, say, an I-beam or a wide flange beam. So trying to find the moment of inertia about that. So, and it depends if you find the moment of inertia about, say, some axis, or if it's about the centroid. So that might be another thing to look over. So then, I guess the last thing that I can think of would be a truss. So solving a truss using either method of joints or method of sections. Because if you have a system and every connection is pin connected, and it asks you to find this force in that member, you don't want to solve method of joints, solving, slowly going through. You might want to just take a section cut and solve for it then. I know I think it was test 2, he said he wouldn't be providing a space truss on that test. I didn't hear him say anything.
I asked him and he said no. Like he straight said no.
Okay, yeah. But yeah, so I guess these would be 3 things that we didn't cover today that may be worth checking into before your test.
Could
Yes.
you just like briefly explain zero force members?
So yeah, we can go over that real quick. So we'll use this example here. Say we have a pin and a roller. Let me get rid of this now. Say we have a force here. We have a force here. This is force F. This is force P. So can anyone, actually, let me move this here. So does anyone see any zero force members? That one.
The one, like, a vertical
I didn't mean to like.
Yeah,
No, that was,
like the vertical one
to the left of the roller. So this one here? So you're saying that's a potential zero force. So what does everyone think? Yeah. So if we look at it, so if we say this is node B, if we draw node B out, we draw all the forces in tension. So we have one going to the left, one going to the right, and we have one going vertically. So if we sum the forces in the Y, we only have one member in the Y. So there can't be a force in this one because there's nothing to counteract it. However, now, does everyone see that? But so the reason I moved the force was that way we had a zero force. So if we had a force here then, we couldn't say that's a zero force member because there is something to counteract it. So does anyone see any other zero force members?
Would it be the same for the
So what does everyone think about here? No. Yeah, because if we draw, say this is node A. So, yeah. Node B, node A. Yeah, so we have one in tension this way, one in tension this way, and then two going this way. So we couldn't say either of these are zero force members because there's potentially something to counteract it. So potentially the only zero force member would be that one there. Yeah. Any other questions?
So when you're doing like a truss problem or a problem like this, and like you find all the forces at A, so if one of them is in compression and you change it, when you go to the next one, if you use that same force, do you use the negative or do you use the positive?
It's a good question. So, for example, let's say we determined, this is AD, we determined AD was in compression. The tip that Medeiros provides is you do your revision bubble, you cross it out, and you change the direction. So compression goes into the joint, tension pulls away from the joint. So now let's move over to node D. And let's say all these other ones are in tension. We haven't solved them yet. So this is in tension, this is in tension, and this is tension. Which direction should you draw AD?
You should draw it up into it.
Yeah, so we draw, since it's under compression, determined at node A, you would draw it into the joint. So therefore, this is AD. So when you sum the forces in the X, so even though it's compression and you list it on the test as a negative answer, when you sum the forces, you go off the direction of the arrow. So you sum the forces in the X, you have a positive AD. You sum the forces in the Y, you have a positive AD. So the negative answer is just for when you input it into the test to indicate it's under compression.
You draw
Good question.
compression for node D because you got it in compression in node A.
Yes. Yep, very good.
Could you just state the rules for zero force members?
Yeah. So I can kind of go over them. I can't like state the exact, I don't have it memorized, but I know the rules for it. So I believe rule 1 or rule 2, I don't know the exact order of them, but so one of them was if you have, I believe, 2 bars that are collinear, and you have one acting at some angle theta. So it's a 3-joint node, and you have 2 collinear, one acting at some angle theta. Then the one acting out of the plane, so out of these 2, would be zero force member. So that's kind of what we had here before we put this F here, was since these 2 are equal and opposite, you can't have a force to counteract it. And then the other one was, say you had a system that looked like this, and there's, say, something here, and say a roller here or something. So if we look at these two, there's only two members. This can only be in the x direction. This is in the x and y direction. So, and they're acting at some distance or some angle theta. So this has a y reaction to it, but this one does not have a y, so it can't react in the y direction. So if you were to sum the forces in the y, you would only have this component. So therefore, both of these would be zero force members. So those are essentially the rules. Just go back and look at his notes, and he'll kind of give you like the formal rule for it. But just look out for a member that acts out of the two collinear and two acting at some angle theta. And like for clarity, you could always draw them. I could have drawn it to where they're perpendicular, and it may be a little bit more clear. Because this only has an x, and this only has a y for the direction. And those are the two rules for zero force members. Any other questions before we wrap up? And then, did everyone get a survey as they walked in? I guess, who did not get a survey? Yeah, so it's just a kind of, I guess, a survey. Not sure how to explain it more than Everyone else get one? You guys get one? Yeah, if you just want to leave it on the table at the end. Yeah. And then we still have about 8 more minutes, so if anyone has any other questions about any of the problems, question in general, thank you. And I believe let me just, because at the top it asks for you the session number. It is session 58, so the two bubbles.